Alright, hello everyone. Welcome back to another video by Random Coder. So, it's been a while since I made a video, but today we'll be learning about how to program your own binary index trees, or otherwise known as Fenwick trees. So, basically, what a binary index tree is, or a bit, or a BIT, is that it's commonly used to quickly execute range update queries. So anything where you need to update values over a range and then query it, this is the data structure that you want to use. So one application could be, for example, you have an array here. So this is your array. Oops. So this is your array. And what you want to do is you might have queries where you want to get the sum of a range. So for example, here we might want the sum of index 1 to 3, so 0, 1, 2, 3. So 1 to 3 is this sum. If you add it up, that'll become 22. Maybe you want to increment the value at index 2 by 5. So this goes to 14, and then you might want to take the sum of the range from 2 to 4, so 0, 1, 2, 3, 4, 5. So sorry, 2 to 5. So you would have this range, which would get you the value of 27. Now, the trivial thing to do is, of course, to loop through the array every time when you find your sum. So that means your sum query is going to have a complexity of O of n. And your increment query is going to have a time complexity of O of 1, which may seem good, but most of the questions that you encounter with these will ask these queries more often. So your time complexity here is not very optimal. So what we need to do is we need to come up with a better time complexity than O of n through the use of some pre-processing and uh, intelligent array partitioning to solve this issue. So over here, we have a quick example to explain what we need to do for a binary index tree. Okay, so here I just put our original array here. That was from the previous page above here. And what we need to do is, for a binary index tree, we're going to represent it as an array. Even though it's called a tree, we're going to represent it as an array. And what happens is we're going to define bit at k. So the position at k is going to be one index first of all, because it'll be easier for us to calculate values with one indexed arrays for now. And what we're going to define bit at k as the sum of values from position 1 to k minus f of k plus 1. So what this is f of k is a function I'll explain in a second, but in simple ways we can visualize this. So after we visualize this, let's zoom in a little bit. What we'll see is that this segment, the sole 8, so 8 as a segment goes here. This larger segment with two values goes here. So basically the sum of these two. And then this value, 9, goes here. This value, which consists of 4 values, goes here. And then 1 value goes here, 2 values goes here, 1 goes here, and then all of it goes here. And what you may notice is that once we have the sum of these ranges, we can construct any single range with at most log n operations. So for example, if we want, let's just say we want the range from, let's use yellow here. If we want the range from position 1 to position 7, that is equal to this range plus this range plus this range. So as you can see, instead of looping through 1, 2, 3, 4, 5, 6, 7 values to get to this sum. We only need to add 3 values together to add up to this range, which is obviously more efficient than the naive algorithm. So what this f of k is, function f of k is defined by the greatest power of 2 that divides by k, right? So as you can see here, the sum of values from 1 to the greatest power of 2 that divides 1 is going to be 1. So it's just this value here. And this function has a very easy way to be found with bitwise operators. So what we can do is we can bitwise and k and negative of k. And how this works is, say we have a binary number such as 10110. We know that the greatest power of 2 that divides this number is going to be 10 in binary. And that is because the greatest power of 2 the greatest power of 2 that divides this number is equal to 2 to the number of 0 bits, number of trailing 0 bits behind the last one, which is 1, so it'll be equal to 2. And that is the way how binary works. So basically our problem that we're trying to find is we just need to find the number of trailing zeros behind the last 1 bit, and that'll be our greatest power of 2 that divides by k. How we do that is, how this works is negative of k is equal to the inverted k. So we invert k first, and then we add 1 to that. So negative of k is equal to the inverted bits of k plus 1. And how that works is, every single bit, since the trailing zeros, it will be inverted to ones. So for example, trailing zeros will be inverted to ones, and the last one will become a 0. So what happens is, when you add 1 to that, this one goes to 0 and it carries the 1 out there, which will chain reaction to the rest of the zeros and make them back to zeros. And then there will be a 1 left to carry at the last 1 bit. So then that'll become a 1. And then we have our number that we need. So quick demonstration, say our k is, let's just say our k is equal to 6. So we have, so the binary will be 110. And what we need to do is, first we invert k, so we get 001, and then we add 1 to that, so we get 01, and we AND it with this number, and we get 10. So 10 in decimal is 2, and that is the greatest power of 2 that divides k. So that is how we're going to implement function f of k. Next, let's talk about how we actually can find the sum. Okay, so in here, as I gave an example out previously, the sum of 1 to 7 here is simply equal to the sum of 1 to 4, which is this segment, plus the sum of 5 to 6, which is this segment, plus the sum of 7 itself, which is that little segment up there. And if the sum query is not starting at 1, we can take a similar approach to prefix sums. So if it's not starting at 1, then it's simply 1 to 7 minus 1 to 3, and that'll get us the segment from 4 to 7. I think that's pretty self-explanatory, because say we take the sum of this long segment, then if we subtract it, the sum of this segment, then our results will be the sum of this segment, which is what we need. All right, so let's talk about how we can get the sum of 1 from index 1 to some arbitrary index that you might want. And how you do that is, if we go back Yeah, if we go back up here, now I'm going to erase a few things real quickly. Okay, but if we go back here and let's just say you want this segment, that'll be this segment plus this segment will get you the segment from 1 to 3, right? 1, 2, 3, and then you have the length 1, 2 to 1. And what we're going to use to find that is, say we are at this position in our binary index tree. So right now our segment ends at 3, so we're at this position. We know that this value needs to be added, right? Because it is the part of the segment that we're at. Well, then we also know that if we add this value, we'll be missing some other value to the left of this segment. And to find that, we need to find the greatest power of 2 that came before this segment that we can add to our sum. So therefore, if we subtract f of k by, so if we subtract this index by f of k, then we'll come here. So in this example, our k right now is at 3. So if we subtract the greatest power of 2 that divides by 3, which is 1, we'll be at index 2, which is this place. And that's the place we need because this place contains the sum of this segment, and that's the one we want. And you'll realize that as you keep subtracting, so for example, if 2 gets subtracted by the greatest power of 2 that divides by 2, you get 0, and that is the end. So we can be guaranteed that we already have a sum here. Now, if we try a bigger example, such as, let's just say, if we have a bigger example, such as k is equal to 7, like the one we have below, what we need to find is, first, we need to add this segment, right? Then we need to add this segment. Sorry. So this segment, and then lastly, we need to add this segment. So basically what we're trying to do is we are just trying to construct a number using powers of 2. That is what this really is. So we need 7, so that is equal to 1 plus 2 plus 4, right? So we're just trying to construct this number with powers of 2, and then we can convert that to the segments that we want, which is 9 plus 7 plus 30. So this sum right here is going to be equal to 46. So that is how we're going to find the sum. And then now we have the sum ready, we can take a look at how this could be implemented. So for example, we have our result value. Then while this index is greater than or equal to 1, we add this bit, right? And then what we do is we go to the next previous segment that we want, which is just basically k minus f of k. And that is what this code does. At the end, we return result, and we have our sum. Then the next problem we need to solve is updating values in the array. So for example, we need to update a value. For example, let's just say at index 4, we want to update the value so it is, and it increments the value at index 4 by 3. So 0, 1, 2, 3, 4. So it's this value right here. We want to increment this value by 3. Now what we need to do is we need to change every single segment in this binary index tree that is affected by this value. So if I want to highlight that, it can be seen that the value affected is this segment right here. This segment is also affected, and then this giant segment at the end is affected. And basically, we only need to update these 3 segments to have our binary index tree array be synced to our original array. So how do we do that though? And then we're going to use a very similar technique to sum, except this time we're adding instead of subtracting. So right here, my k is going to be 4. So what we need to do is, of course, first we need to update the value at 4. So we update that. Then we need to update the value here. And how you do that is you get k plus f of k, right? So when you get k plus f of k, you get this segment plus 1, because right now this is at position 4, but really 5 because it's 1 indexed. So you get 5 plus 1. So when you get to position 6, you update position 6 as well. And then after that, you update position 8, which is this position right here. But technically, it is 7 in this representation. But since it's 1 indexed, it's going to be at position 8. So once you update these values, your BIT array will be completely updated, and you can do the same sum. You can do the same sum function over here. So you can run this. Oops. And the result of the sum will be updated because your BIT segments are updated. So how might you implement an increment function? Well, it's also pretty similar to the sum function. So you just have an index, you have an amount, and then while this index is less than the end of the BIT array, you add the amount to that, and then you update your index so it goes to the next segment that's affected. So now we can go take a look at how this might be implemented in real code. Okay, so in here, I have a binary index tree class, and inside it just has this array called BIT, and that's going to be our array. And initializing it, we're going to initialize it to size n+1 because the array is 1 indexed. And then we have our increment function here, which actually looks basically the exact same as the one I showed in Microsoft Whiteboard. And what we can see here is that all we need to do is we need to add the amount to this index, and then we need to update the index so it becomes the next segment that's affected. And then of course I add 1 here so I can 1 index the index, because I want the user to still be able to put 0 indexed values into the parameters, and then it'll take care of the 1 indexed internally so there's not much confusion. For sum, for the 1 through k situation, we have an end. So first we 1 index this end to make things easier. Then we have this result that we're going to return. Then while this index is greater than or equal to 1, which is basically 0 if you want to think about it in 0 index terms. So while it is greater than 1, we want to add that segment sum onto our resultant sum. And then we update it so we can get the previous segment that is in the range that we want. At the end, we return s, and we have the sum of 1 to e. If the start is not 0, then what we do is we take our prefix sums approach, and then we can do sum at e minus sum at s minus 1. So basically that's equal to, say you have a segment from 1 to 7 again, and then you want to find, say you want to find the segment of 2 to 5. That's basically just equal to the sum of the segment from 1 to 5 minus the sum of the segment from 1 to 1. Right, so that's what it is, and that's what this function does. And then at the end, we have a toString function here, so you can visualize the binary index tree array if you wanted to. And that's it. So over here, we can go test our function real quick. I have a test array that is basically the array I put in the whiteboard. So how you would initialize the array into the binary index tree is at each index I, you can just increment that value by this array value, which will fill the segment tree to be synced with array right here. And after that, we can print out we can print out our binary index tree, which will show this array. And then we can print out the sum of 2 to 4, so 0, 1, 2, 3, 4. So that's just basically 9 plus 6 plus 9, sorry, 9 plus 6 plus 3, which will be 18. And for example, if you want 2 to 5, that should be 22. And if we run that, that'll be 22. So that's basically how binary index trees work and how you implement them. So if you liked the video, please give it a like and subscribe to my channel. And happy Thanksgiving. I'll see you next time.